MAYO is a submission with these 5 people. So myself, Fabio, Sofia, who is sitting over there, Basil, and Matthias. Okay, so the MAYO trapdoor is very, very similar to the oil and vinegar trapdoor. So it's also just a subspace O on which all your equations vanish. But the difference now is that this space O is much smaller. So it used to be the case that the dimension of this space was equal to the number of equations that you have. But in the case of MAYO, the dimension is much, much smaller. And this has 2 benefits. So first of all, because this space is smaller, it's harder to find this. So you need to have fewer variables to hide the space. So I mentioned earlier that the complexity of these key recovery attacks were exponential in n minus 2 times m. But now if you have a smaller space, it becomes exponential in n minus 2 times O. So if O is smaller than m, the number of variables that you need shrinks a lot. So you can have a smaller system, which is good for efficiency, of course. And also the public key becomes now much smaller. So now it's the complex, like the size is proportional to O squared times m instead of m cubed. And if O is much smaller than m, this is a big improvement concretely. But yeah, why didn't oil and vinegar use a smaller space? Well, it's because now if the space is too small, the signing algorithm doesn't work anymore. So I mentioned earlier that when you sign, you end up solving a system of linear equations, and the degrees of freedom that you have comes from the dimension of your oil space, and the number of constraints that you have to satisfy is the number of equations. So if the dimension of this space is now too small, you'll end up with a linear system with too many equations. So it's very unlikely that this system of equations has a solution. So signing doesn't work anymore. So in MAYO, we had to find a solution to this problem. And the solution is to start from this small space, this small set of equations, whose oil space is too small, and then we whip it up into a bigger system of equations. So still the same number of equations, but more variables. And we do this in such a way that the oil space also blows up. So we increase the number of variables by some factor k, and then also the dimension of the oil space goes up by a factor k. And now you have a new system of equations with a bigger oil space, and then we use this system of equations to solve to sign messages. So like a naive thing that you could try to do is you define the bigger map p star to just be the sum of k times the same functions on independent inputs. So of course, if p vanishes on a space O, then this p star vanishes on this space O to the k that consists of all like this k vectors of O concatenated. If you plug this in, then each of the summands becomes 0, and then clearly p star vanishes on this space. And also this space now has dimension k times O, because you go up by factor k. So you could use this p star as your public key and make signatures. But unfortunately, it turns out that this is not secure. It's too simple. But yeah, we have to fix things a little bit. So one problem is when you are like adding the same system to itself, that introduces a weakness. And we solve this by adding these E matrices. So E stands for emulsifier or egg, because it like prevents your map from collapsing, basically. So yeah, we add these. Yeah, I don't think you can see the pointer, but we add these E matrices. And also there was a problem that since you're adding independent functions, you can do these generalized birthday attacks. And to prevent this, we need to have some cross terms. So we also add these other terms. So for every pair I and j, we have another matrix E ij, and then we add this differential. And this differential will also vanish if the xi and xj are in your oil space. So yeah, this is the new p star that we will use, and you can check that this vanishes on the same O to the k oil space, which is now a factor of k bigger. And the assumption is that this map is still pre-image resistant. So this is a new assumption that, but yeah, it seems to hold for all we know. Then the security analysis. So if you assume that oil and vinegar maps are indistinguishable from really random maps, which is an assumption that we're happy to make because this has been studied for a very long time in the context of the oil and vinegar signature scheme. And in addition, if you have this new assumption that this whipped up map is still preimage resistant, then you can prove that the signature scheme is secure. And in particular, this means that we prove that by giving away signatures, you don't leak any information. This is new in this context because you cannot prove this for the oil and vinegar scheme itself, but for this whipped up version, you can prove it. So that's something that we gain. Okay, so then parameters. So on the left-hand side, we have the oil and vinegar parameters that I talked about. And on the right-hand side, we have 2 parameter sets for NIST security level 1. One is aiming to have a very small public keys and signature size. That's MAYO 1. And then the second one, MAYO 2, is focused mostly on getting smaller signatures and still have a somewhat small public key size. So for MAYO 1, the public key size is only 1.1 kilobytes, so it's really much smaller than oil and vinegar. So that's like the problem that we solve with MAYO. The signature size is a little bit bigger, like a factor 2 or 3 bigger than oil and vinegar. And for MAYO 2, we do a slightly different trade-off where we have a somewhat larger public key, so 5 kilobytes, but smaller signatures, like 180 bytes. And yeah, really, if you wanted, you can have many other trade-offs, like trade-off between public key size and signature size. By varying this factor k, by varying how much you whip up your map, you can control this trade-off. This is again the graph with all the submissions. So you can see now we moved to the left. We have smaller public keys. We've also moved a little bit up because the signatures are a little bit larger. And maybe if you're wondering that lonely dot there in the middle, that's key signs. So they're really exceptional in the sense that they are very small signatures and public keys. But we also, in theory, you could have this five-part API, and we also implement this under the hood. But you can see that now it's much less extreme in how much you can gain by factoring the signing or the key generation in multiple parts. So in the submission document, we only submit one version where we put the key expansion and the public key expansion as part of signing and verification, respectively. But yeah, of course, if you were to use this in reality, then you could win something by doing it this way. So this is still work in progress, by the way. We hope to improve on this in the near future. But for now, these are the numbers in the submission document. And signing is like 100 microseconds, and verification is 30 microseconds for the security level 1 parameters for big Intel CPUs with AVX2 and AES hardware support. Oh yeah, and maybe I should mention that these key expansions, they really heavily use AES. So here on a big Intel CPU, this is quite fast, so there's not too much of a difference between the expansion part and the actual signing part. But if you use like an embedded device where AES is much more expensive in comparison to just doing arithmetic, because you don't have the hardware support, then these expansion algorithms get much more expensive in comparison to the signing. So in those kind of situations, it could really make sense to only do this expansion part once and then store the bigger public key, at least if you have the space for it, and then and then use this bigger key for all your signing and verification operations. But yeah, if you put them in one big signing and verification algorithms, then you have like 300 microseconds signing and 45 microsecond verification. So it's still very fast. Okay, so then advantages and limitations. So we have some of the same advantages as oil and vinegar. Namely, the signatures are quite short and it's still very fast. But A new advantage is that the public keys are also quite short. So you could have keys as small as 1.1 kilobyte. But the new limitation is that we use this new hardness assumption where we assume that if you whip up this map and make it bigger, then you still have a pre-image resistant function. So this is something that requires script analysis, but many people have been looking at this already, and so far it seems fine, but the future will tell, of course. So yeah, that's it. So any questions?